Plumbers will keep their jobs, except they're going to be plumbing light pipes. Wow. That is an incredibly vivid thought adapted from AI pioneer Geoffrey Hinton. It's the kind of statement that immediately forces us to stop thinking about artificial intelligence as just this invisible software floating up in the cloud, and really grounds us in the physical, tangible reality of our future hardware. We aren't just building new code anymore. We are quite literally going to be laying down pipes of light.
Welcome to today's Explainer, where we're going to unpack exactly what that means. We'll be looking at a grand-scale vision proposed by Professor Dr. Guy Lakeman. He calls it the University of Superintelligence. We're going to explore his blueprint for a globally collaborative AI architecture, a system that moves us away from fragmented, wildly power-hungry models and towards a remarkably efficient, light-powered global brain. All right, here's our roadmap for today. We'll be covering the AI energy problem, the University of Superintelligence, specialized AI silos, the photonic hardware revolution, and finally, global breakthroughs in photonics. So let's jump right into Section 1, the AI energy problem, looking at waste and competition. Let's start with the root of the issue. Dr. Lakeman presents a pretty stark view of our current landscape. He argues that today's trajectory is totally dominated by tech giants racing to build incredibly energy-intensive models. He actually terms this a multiple energy-wasting competition led by self-appointed elites. What he's arguing here is that this fragmented approach just leads to geopolitical brinkmanship, basically fogging up the internet with wasteful political competition instead of unifying our resources for actual human progress. Dr. Lakeman makes his stance on this point abundantly clear. He writes, "Say goodbye to greedy bastards trying to sell crap and strive towards quality of life." Now, setting aside the colorful language for a second, his underlying thesis is highly pragmatic. He argues that by 2026, these systems are going to possess competent, greater-than-human intelligence, and rather than using these systems as profit-driven killing machines, this intelligence absolutely must be restructured to serve global evolution and society as a whole. For you and me, this means an AI ecosystem focused on solving actual global challenges, like ecology and infrastructure, rather than just pumping out corporate revenue. Moving on to Section 2, University of Superintelligence, a global vision. So what is his proposed solution? Well, check out the central core of this conceptual diagram. It maps out a dedicated collective of zoned research. You have to think of this not as one giant corporation server farm, but more like a collaborative global infrastructure. It's very much like CERN in particle physics or the International Space Station. Different AI domains, like STEM, humanities, law, and ecology, are intricately connected through a central core. This totally avoids the duplication of effort and the massive energy waste you get from competing monolithic systems. To make this actually work on a computational level, Lakeman introduces what he calls the Large Concept Model, or LCM. Instead of building one impossibly massive large language model that has to know absolutely everything in the universe and therefore burns immense amounts of power for every single query you give it, the LCM architecture utilizes many dedicated, highly specialized LLMs. It's like going to the hospital, right? You wouldn't ask a heart surgeon to fix a broken tooth. By routing tasks only to the specific silo that specializes in that exact knowledge, you drastically cut down the computational overhead and, as a result, the energy wastage. Which brings us nicely to Section 3, Specialized AI Silos, Focused Efficiency. Let's look a little closer at how this focused efficiency actually operates in a real-world hierarchy. In a global LCM, these silos don't just sit in isolation. They feed into each other with intense specialization. For example, a government silo fundamentally links to global ecology. Why? Well, because you can't govern effectively without managing resources. Ecology dictates infrastructure requirements, and infrastructure directly impacts climate action. By having specialized AI agents handle these distinct but deeply connected domains, the system operates with absolute laser focus, requiring just fractions of the energy a generalized AI would need to puzzle through the exact same global challenges. Okay, let's pivot to the hardware side. In Section 4, the photonic hardware revolution, computing with light. Because at the end of the day, theoretical software still requires physical hardware. And traditional silicon simply can't handle the efficiency demands of a global superintelligence. Traditionally, GPUs operate on the classic von Neumann architecture, constantly moving data back and forth using electricity, literally just electrons pushing through copper wires. But the future looks totally different. We're looking at photonic chips, like the ones developed by German deep tech company Quant. Instead of electricity, they encode data directly into laser beams.
Through specialized materials, the math is solved natively by the light itself. And the resulting efficiency is just staggering. 30. That is the factor by which the QNT native processing unit lowers energy consumption compared to traditional silicon-based GPUs. Up to 30 times lower energy use, while simultaneously delivering up to 50 times faster performance for AI and scientific workloads. We aren't talking about tiny iterative improvements here. This is an absolute leap in capability. But actually, it gets even better, because these chips compute with light particles, photons, instead of electrons. They completely bypass electrical resistance. And no electrical resistance means zero on-chip heat generation. If you've read the news lately about AI consuming local town water supplies, this is exactly why this matters. Massive data centers today gulp down entire rivers of water and megawatt after megawatt of power just to run the air conditioning and liquid cooling systems. Photonic computing theoretically eliminates that massive, environmentally taxing cooling overhead altogether. To put the sheer density of this into perspective, think about the number 1,200. A single optical element inside a QANT chip can perform an 8-bit multiplication that would require 1,200 conventional CMOS transistors on a standard silicon chip. Mind-bending, right? It is a completely different scale of spatial and computational efficiency. And that leads us to our final section, Section 5, Global Breakthroughs in Photonics, looking at China and Germany. Now, you might be sitting there thinking this all sounds like incredible science fiction. It is absolutely not. Real-world breakthroughs are happening right now, predominantly led by massive strides in China. Researchers aren't just theorizing, they've actually developed the LightGen AI accelerator at Tsinghua and Shanghai Jiaotong universities, which vastly reduces power consumption for neural networks. We're also seeing photonic quantum chips from companies like Turing Quantum that literally fit into standard data center racks, claiming to accelerate specific AI workloads up to 1,000 times faster. Furthermore, the Shanghai Institute of Microsystem and Information Technology has cracked optical mass production using lithium tantalate, which lowers costs and intentionally bypasses reliance on restricted Western semiconductor equipment. And the physical supply chain is shifting super fast. Over in Jiangsu province, the CHP hub in Wuxi is now operating a national pilot line capable of producing 12,000 thin-film lithium niobate photonic wafers every single year. Previously, China's localization rate for advanced photonic chip supply chains was under 5%. Today, with companies like Robotechnic leading high-speed assembly and testing, they're creating a formidable closed-loop system for fabrication. Meanwhile, over in Germany, QANT is proving that this technology is ready for immediate deployment. The beauty of their native processing server is seamless integration. It uses standard PCIe interfaces and connects flawlessly with the AI software stacks developers already use every day, like PyTorch and TensorFlow. In fact, this hardware is already operating in high-performance environments right now, like the Leibniz Supercomputing Center, running visual AI and complex scientific simulations today. So, from Dr. Lakeman's visionary collaborative University of Superintelligence all the way down to the atomic level of encoding lasers into thin-film lithium niobate, the roadmap is clear. We are shifting from electrons to photons, from competitive waste to specialized efficiency. So the question we have to leave you with today is this. Will computing with light be the ultimate key to unlocking the collaborative, energy-efficient superintelligence we so desperately need to navigate our future? The plumbers of light are already out there working. Let's see how fast they can build it.